presentation was a bit too fancy for you, you can be glad I only have one slide with formulas on it. So I hope it's a little easier to follow, at least for me. So I'm going to talk about optoelectronic characterization of organic solar cells. So this time no mobile ions. It makes the whole story a bit easier. It's what I present here is basically the results of a review study that we wrote and published at the beginning this year. And the idea of this study is that it helps you interpreting measurement results when you have it. So let's start. Oh, now it doesn't work again. Ah, here. Now it works. Okay, good. Let's start quickly explaining the simulation. So now comes the slide with the formulas, but it's very easy. This is just drift diffusion. So first what we do is we calculate transfer matrix formalism to calculate where is the charge, well, where is the light absorbed. And so we calculate interference patterns. And then from that point we know where is the charge generated, and then we solve drift diffusion for electrons and for holes. So you see here the drift part and the diffusion part in the bottom equation. So here, and here you see the equation that governs the generation and recombination of charges. So charges either recombine or they generate or they flow away. And so basically we solve this, and then we add Poisson equation, and this is what we solve, how we describe the solar cell. We furthermore add an external series resistance, and this is quite important if you do drift diffusion simulations and if you want to compare it with measurement, because in the measurement you always have a certain series resistance, what I show here. So here we solve the drift diffusion part, and outside there is an external series resistance. And this series resistance is important because you can never neglect it in the measurement. Because, for example, if you have your layout at a certain point, the current needs to flow laterally in your TCO. And the lateral current flow in the TCO, and we know TCO is not that conductive, always creates a certain series resistance. Furthermore, when you measure it with certain measurement devices, you also have some internal resistance of the measurement devices. That's why if you want to compare it, it's very important. All right, so let's start with the characterization review. So what we did is the goal is now to use our simulation tool to simulate various different techniques to understand how these techniques work and what you can learn from these techniques. But first we need to define some cases. So we defined in the paper 11 cases. I only show a few of them here. So we have just a base case of an organic solar cell. There's one layer, a bulk, two contacts. Very easy, no traps, nothing. And then we have a case here, what we call extraction barrier. Here we add another small layer and add a barrier for the extraction. So the electrons need to overcome this barrier to be extracted. And you could imagine here that could be an organic solar cell, and you form some aluminum oxide on the surface. This creates exactly such a barrier. Then we have one misaligned contact. For example, if you just put a metal there or something, that creates you here a contact that is just much lower. So what you would expect is then the built-in voltage is decreased. Then we have one case with lower mobility, which is decrease electron and hole mobility simultaneously. There is a case where we have much higher Langevin recombination efficiency. And here we have two cases with traps, one in the middle of the band gap. Here we expect Shockley-Reed-Hole recombination, and here with only shallow traps, here there's no Shockley-Reed-Hole recombination. There we mainly see the dynamics of charges getting trapped and being detrapped. And then we have here another case with doping and some further cases. I won't go into detail here. All right, so first we simulate an IV curve to see how the device looks and what the influence is of our cases on the IV curve. And this is you see here. So the black line is always the base case. So this is where you compare it to. So you see the non-aligned contact, what I said before, has a lower built-in, so it's kind of just shifted to the left. This is what we expect. The extraction barrier creates such an S shape here. And when you're a bit familiar with interpreting IV curves, you know an S shape usually means something is wrong with your contact. And also here, the only case where we have an S shape is the case where we have an extraction barrier, means something is wrong with our contact. And then here, when you vary the mobility or the recombination, you see like that the fill factor is going down a bit. Same counts for when you add traps, no matter if they're deep or traps in the middle of the band gap. You see in both cases here, the fill factor decreases, and here also that the current decreases a bit. What might be a bit surprising to some people is that also when you add doping, the fill factor decreases and the current goes down. This is what you see here in this in the brown curve, this here. This is simply because we are simulating here an organic solar cell, and an organic solar cell usually has quite low mobilities. What means when we add doping, the electric field is screened, and the charges cannot manage to escape. They're still generated, but they cannot escape because charges in an organic solar cell need an electric field to escape. So that might be a bit surprising here. All right, so let's continue with the dark IV. That's also a very simple steady state technique where you just measure the current in the dark. And what you see here is we always get this shape. So here in the reverse direction, this is the parallel resistance, what we see here. There is one case where I added an additional parallel resistance, so that makes the parallel resistance a bit smaller. So you could imagine just a ohmic shunt in your solar cell, and you see that here in this case in the lower left, here you have a high reverse current. So this is clearly the shunt resistance. You always see this in dark. So if you want to extract the shunt resistance, it's recommended to use the dark IV in reverse direction. What is interesting when you look at this shape, it has been mentioned before in many talks, is you can extract the ideality factor from this slope. So this slope here the ideality factor, information about the ideality factor is inside. And when you now change the mobility or the recombination, what happens is you only shift the whole curve, the slope remains the same. Except in one case, this is the case where I have added Shockley-Reed Hall recombination with traps in the middle of the band gap. This is this green case here. So here you see we have clearly a different ideality factor. So on the lower right here, what we did is we calculated the ideality factor from all these cases, and you see there is only one case, the case with deep traps, the green case here, deep traps, where we have an ideality factor of approximately 2. Just in reality, when we have recombination and injection and all the stuff, the ideality is never exactly 1. But it's approximately 1. And here you can clearly see in our cases, we can use this ideality factor to distinguish the recombination type. So this here works very good because you see all the rest is somehow below 1.2. There's another way to measure the ideality factor, and this is what has also been shown today, for example, by Phil, that you measure the VOC versus the light intensity. And we also simulated this. And here we get the same image. We get this curve that has a certain slope. When we change parameters, it goes up and down, but the slope somehow remains the same. Except the case with deep traps, what we can clearly see here is there is a different recombination type. So there's a different ideality. When we plot the light ideality factor, as we call it here, you see the same image. There is one. It's the deep trap, the case with deep traps, that has an ideality of 1.8, and all the rest is somewhere around 1. So these two cases are apparently quite stable, and you can extract the recombination type, so like the dominant recombination type, from these measurements. So that's also something that we can learn. Okay, let's go to a bit more fancy techniques. A technique that is very popular for organic solar cells, and it's also been used for perovskite, is so-called photo-CLIF. It works like this. You first create some light in your solar cell, and then you have a voltage ramp to the negative. So what you see here, this is the voltage. So you have a linear ramp to the negative direction, and what you get is you get a current. Sometimes you get a peak, and you get a constant displacement current. This technique is often used to measure charge carrier. Estimate the charge carrier mobility. Can you hear me? Okay, and you can measure also, you can extract, in the case of dark CLIF, you can extract the intrinsic charge carrier density. So for example, if you have some doping. And this is what we see on the next slide. This is what you can learn from it. So you just integrate here the charge that comes out of the solar cell, and you get an amount of charge carrier density. Either when you have created them by light, then you just get the charge density, or you get the dark, the doping density. So when we do this in the dark, what you notice in all upper cases, basically we see only RC effects. So here, in this whole line, what you see here is only RC effects. You see a capacitor that is being charged. And that means there is no charge inside the device, because we do this experiment in the dark. There is no charge that can be extracted. In the lower case, there is one case where we extract something, and it's the case of doping, high doping density. You see there is a peak and there is charge being extracted. So what one can do is one can just integrate this current, and when you integrate the current over time, you get a charge, and you divide it by your device volume, so you can estimate the doping density. When you look at here, we extracted the doping density. Here you see it's about 10 to the 16, what we extracted in this case. But it's much lower, because what we put into the simulation was 10 to the 17. And it's quite clear, with this experiment, we cannot extract all the charge that was in before. So it's important to know that we can get a lower estimate of the can assume that the doping density in fact is high. Lower estimate. All right. So now let's do this experiment with light, which is a bit more interesting, because here we have, in all cases, we see such an overshoot. From this, the position of this overshoot somehow depends on the mobilities. You see, there is one case with the low mobilities. It's a case in the middle. This case here. Here, this peak is much slower. And this is why this is the effect that this C-lift technique is exploiting, with this simple formula saying if this peak time is higher, it takes longer for the extraction, then the mobility is lower. And this is what we see here quite clearly. What we also see is the case with deep trap has a much slower overshoot, and a lower overshoot, and we can understand this as with the deep traps, the charges can efficiently recombine, and therefore they can be extracted. In the case with the shallow traps, the opposite is the case. Kind of the traps protect the charge carriers from recombining. That means once we extract it, we have more charge that we can extract. What we did in this case, we used this simple C-lift formula and analyzed what kind of mobility do we get out, and we plotted this here, and the fine line, in case you can see it, the fine gray line is the mobility that we put in. And you see in all the cases we get more or less the order of magnitude of the mobility that we put in. Also here in the case, you cannot see it, but there's a small gray line here. Also in the case of the low mobility, we get more or less the mobility that we put into the simulation. So also this technique is quite useful to measure the mobility, but one needs to be careful. For example, in perovskite solar cells, what you mainly measure is the mobility of your contact layers. You don't measure the mobility of the carriers of the perovskite, because they're too fast. Basically, you see the contact layers. So this is a bit error prone in the case of perovskite solar cells. How much time is left? Okay. So let's go to a next technique, because I have quite a number of techniques. I cannot present all of them here. But one interesting case is the capacitance voltage. So we do impedance spectroscopy. So we do here is we do impedance and we vary the voltage. Usually what you get is you get a peak somewhere around the built-in voltage or a bit below the built-in voltage, and then the capacitance collapses. So this is also what you get here in the black case. And what is interesting is that this peak is usually independent of the frequency that you use for the impedance. What you can see here is this technique is very useful to probe contacts and injection. Because the only two cases where this position in peak is really changing are these two cases here, where we have an extraction barrier. Then it takes a higher voltage until we have injection, because, well, our extraction barrier is also an injection barrier. And also in the case of the lower built-in voltage, so the misaligned contact, also here it takes a lower voltage to inject. All the other cases here, you see the voltage is fairly, the peak is fairly at the same voltage. And when we plot this now, the voltage of the peak, here we clearly see it's these two techniques. It's these two devices. It's the barrier and the non-aligned contact that have another voltage. The rest is in a similar regime. So capacitance voltage cannot be used to extract like one particular parameter, but it can be used to study injection. So for example, we had a case of an OLED that is degrading, and we studied the CV in different cases, and we could see that here the peak is shifting. And so from that we concluded that something on the interface is happening because there is a higher voltage required to inject charges. So that's more a qualitative view. All right, let's quickly look at this transient photovoltage before I move on with the more comprehensive story. This is transient photovoltage as it's normally done. So you have an offset light, small light pulse, and you measure the voltage decay. And what we do is we just did the same experiment, and what you then normally you plot it against the open circuit voltage, for example, as what we do here. And so here is then the charge carrier lifetime. And what you see here is, first of all, it doesn't behave as it's expected, because expected it would behave like this small gray line here. This would be the theory. And you see there's a certain deviation of the theory. And this is also related to what the previous speaker has shown this morning, that we have a capacitive decay of this signal. So I recommend to be like very careful with interpreting these kinds of techniques. And here it's very difficult to learn something, or one needs to be very careful to learn something from these lifetimes. Okay, so I need to skip some of other techniques that I had in here. You see, there's quite a few. The good thing is about this publication, you only need to look at the pictures, because the pictures already tell you the full story. When you have a certain technique you want to analyze, look at the picture and you can already find out what your effect could be. So what I've been talking about now is mainly about, let's say it's a qualitative analysis. So you have certain measurements and you want to interpret it, and you don't want to have it in detail. Once we want to go to a more qualitative picture, let's say understanding a solar cell with all the numbers, so extracting all the parameters, knowing exactly what the mobility is, we need to go to numerical simulation. It's not as easy as in silicon solar cells, where you can do some experiments, you extract some parameters and you're done. All the parameters are highly entangled, so you need some numerical drift diffusion simulation to extract the parameters. And this is what we did in the next step. So this is we analyzed a PCDTBT PCBM solar cell, so it's classical organic solar cell, and we performed all of these measurements I showed you before and many more, and we did simulations, and we used fitting algorithms until the simulation and measurement matched in all cases to extract one set of parameters. And it looks like this here. So this is the first graphs. You see the IV curve. Actually, this doesn't really match perfectly. So you see the red curve is the simulation, whereas the black line is the measurement. There's a certain deviation in here. And we attribute this deviation here to Onsager-Brown dissociation, so voltage-dependent charge carrier generation, what we did not take into account in our model here. You see the dark IV fits very, very nicely, so especially like this curve here and the series resistance, it matches nicely, and also the parallel resistance here matches more or less. The reason here is that we use just a simple ohmic parallel resistance, whereas in the real world, I guess the parallel resistance is not really ohmic, but nevertheless it fits more or less here. Also, we managed to describe VOC versus light intensity quite perfectly, and also the JSC, so the short circuit current versus the light intensity over quite a broad range. So let's go to impedance and transient techniques. So also the capacitance voltage we can reproduce more or less. You see here there's a certain deviation. The capacitance here collapses a bit faster, but I think that's fairly okay. When we look at the conductance versus the voltage, it's also the same. It matches quite well. We can also reproduce the capacitance frequency. So you see here two voltages. So once it's at minus 0.5 volt, once at plus 0.5 volt. And so here you can also describe that the capacitance is higher in forward direction and that it increases slightly. It doesn't due to traps. The capacitance increases, and also charge extraction here at the bottom we can describe. So in charge extraction you have C, and you extract the charges after you have turned off the light. Then there's some more techniques. DIT, this is actually Doric Injection transients. It's usually performed on monopolar devices, but here we just performed it at the solar cell, so voltage pulses, we just simulate the same. Also this matches quite well. We simulated OCVD. Here it fits almost that nicely that you don't see the measurement anymore. So this is open circuit voltage decay. It has also been shown this morning. We just keep the device at VOC, and then we turn off the light, and we just measure how the voltage collapses over time. And you see here this is logarithmic time, so this is it lasts over quite a broad range of time scale. We managed to reproduce it. And the lower two graphs are transient photocurrents. So just you turn on the light, you flash the device, it's a light step, and you measure how the current goes up and how the current goes down. And also here we managed to describe both curves here quite nicely. And last but not least is CLIF. Also the CLIF here works quite nicely. What you see is that the peak, well, first of all, there's no peak in the dark case, and in the light case there's only a small peak. And this small peak indicates already there in this device, in this material system, we have quite a high recombination. All right, so that's the full picture, and the difficulty now, of course, is to get such a full picture, because you need to do quite some fitting until you have it, because there's quite many parameters, and we only use one set of parameters to recreate this. The problem is when we only use like one IV curve, and we reach a good fit, it's, you cannot be sure that you really extracted parameters, because it can also be pure coincidence that the IV curve fits. And making an IV curve fit is actually quite easy. Therefore, we try to combine as many things as possible so we have more information to fit. So the parameters that we extract are the following, so you get a bit an idea of what we work with. So we have a band gap. Well, a thickness we already knew, but we have a band gap, we have the injection barriers, then there's a density of states, Langevin recombination efficiency. Also, that these systems have usually a Langevin type, so the efficiency is kind of 1. Then we have a permittivity, then there's electron and hole mobilities, and some trap parameters like a trap density, trap depth, and like capture rates, how fast these traps capture charge carriers. What's interesting here is that we have actually quite a simple model. We use constant mobilities, we use single energy level, discrete energy levels for the traps and also for the transport. There is no doping, there's ohmic injection, and that's quite, to me, I was a bit surprised to simulate a full system with such easy assumptions. Okay, what we often do is to calculate the correlation matrix to understand how unique is our fit. And correlation is expressed this way. If you plot two quantities versus each other, 0 means non-correlated. If it's -1, it's negatively correlated like this. If it's +1, it's positively correlated like this, or something in between these cases. And when we do this analysis for one IV curve, so we take like each point on the IV curve, and we take the difference between simulation and measurement, and we can calculate this correlation for all the parameters, we get the so-called correlation matrix. And this is how it looks. So you see, these are all the parameters that has been used in the system. So it's quite many. So here's the hole mobility, electron hole mobility ratio, Langevin recombination efficiency, all these parameters here. And in the columns, in the lines here, the same again. And first of all, you see the diagonal is 1. It means the parameter is always correlated with itself. That's good. So the hole mobility is perfectly correlated with the hole mobility. But for example, what you see here is that the electron hole mobility ratio is also correlated with the hole mobility. So if you would fit, so this is just one IV curve. If you would fit this IV curve, your fit would be arbitrary, because you see there's a lot of correlation between all these parameters, and you cannot be sure to extract everything properly. And what we now did is we used the same technique, but we used all the different techniques, so also dark IV, CLIF, CF, and so on. And then it looks like this. So this is Now you see it's not perfect yet. But most cases here the correlation is very low. There's only a few exceptions where we still have some correlation, so maybe we would need to add some other techniques to make this really perfect. But when you compare it with before, there's quite some improvement. So that's like a mathematical proof, what's actually obvious, that the more techniques we use, the more comprehensive our fit is and the more reliable the data is that we can extract. All right, so this is our team. A few people left already and few new people came. I'm sorry, it's not it's not up to date. And thank you for your attention.